All right, so chapter 15 was focused on solutions. A solution is a homogeneous mixture, meaning that its components are evenly distributed throughout. Every solution, remember, has two parts. We have the solute, which is the substance being dissolved, and the solvent, which is the substance doing the dissolving. So a way to remember this is that you put the solute into the solvent. So for example, when salt dissolves in water, salt would be the solute, the water would be the solvent. We should also know that we experience conservation of mass, just like we talked about many times this year, not only in chemical changes, but also in physical changes like dissolving something in water. So the mass of the solute plus the mass of the solvent should get us a mass that's equal to the total mass of the solution, right? So if we have, let's say, 30 grams of solute, sodium chloride, and 100, this would be grams because the density of water is 1 gram per milliliter, 100 grams of water, we're going to get a total mass of solution of 130 grams. Now, a solvent can only dissolve a certain amount of solute, right? The point at which no more solute can dissolve is called the saturation point. So a saturated solution is a solution that contains the maximum amount of dissolved solute possible under the specific conditions of temperature and how much solvent we have available. So for an example, if we attempt to dissolve 40 grams of sodium chloride in 100 milliliters of water, the saturation limit for this amount of water for sodium chloride is 36 grams, meaning only 36 grams maximum of sodium chloride can dissolve in 100 milliliters of water at this specific temperature, whatever that happens to be in this scenario. So that means just because I have the 40 grams of sodium chloride doesn't mean all of it's going to dissolve. Because the saturation limit for this example is 36 grams, we should see 4 grams of that sitting on the bottom, okay? If additional solutes added, it won't dissolve. Now, there was one important test that we looked at to see whether or not a solution is at that saturation limit. In this example, you would see some sitting on the bottom, but that is not always the case, and that is not the way to test whether a solution is saturated or not, because you might not see anything on the bottom and it still be saturated. What if we dissolved 36 grams exactly of sodium chloride in this beaker? We would have hit the saturation for that amount of water, but we wouldn't see any on the bottom. So the way to test, we call it a seed crystal test. And what that basically means is you take a tiny crystal of the solute, a very small amount, could be one tiny crystal, and you add it to the existing solution, and you're going to see one of 3 things happen. If that crystal dissolves, then we know that that solution was unsaturated because there was more room for solvent to dissolve in the solvent. If the crystal doesn't dissolve, then we know that the solution was saturated because that solvent can no longer hold any more solute. If we see crystallization, and we use the hand warmer example in class, if we add a crystal and all of a sudden we see all of this solid come out of the solution like out of nowhere, that means the initial solution wasn't unsaturated, it wasn't saturated, it was supersaturated, which is a very sort of unique condition for solutions where they have more than the maximum amount of solute dissolved than should be in a solution. So that's the seed crystal test that you should know about. Concentration was a way for us to kind of quantify how much solute relative to solvent we have in a solution. So concentration describes how much solute is dissolved in a solution. And the general idea is that the more solute dissolved, the more concentrated, and the less solute dissolved, the less concentrated, or we say the more dilute. Dilute is the opposite of concentrated, okay? For solutions that have a color to them, we can see the concentration easily and changes in concentration by looking at how the color changes. So in this example, this looks like some red food dye in water. We can see that as more and more dye is dissolved in the same amount of water, it gets more concentrated. And then down here with less solute per solvent, on a particle level, concentrated solutions contain more solute particles in a given volume, such as here, and dilute solutions contain fewer solute particles in that same amount of volume, right? It's really important when we talk about, we made a big deal about talking about concentration versus like total amount of solute dissolved. Concentration is always solute per some amount of volume. So it's always important to compare when we're looking at concentration, the same amount of volume when we're looking at how many particles exist in that volume. We further looked at quantifying concentration using a specific formula. So molarity is our specific way of expressing concentration. The formula for molarity is we take the number of moles of solute and we divide by the liters of solution that we have. So these units are very important and specific. Moles of solute versus liters specifically of solution. So as an example, let's say we have a 5 molar solution. What this means is that I have 5 moles of solute per every liter of solution we have. Knowing that I have a 5 molar solution doesn't necessarily tell me how many liters of solution I have, but it does tell me information about if I had 1 liter of solution, or for every 1 liter of solution that I have, there would be 5 moles of solute that are dissolved in there, floating around. And again, molarity only describes concentration of the solution. It does not tell you how much total solution we have, right? Nor does it tell you how many total particles or moles of solute are floating around in the solution, okay? So I could have, let's say in this example, I could have 100 milliliters of a 5 molar solution, or I could have 5,000 milliliters of a 5 molar solution. They both have the same concentration. I'm going to have more total moles of particles in that solution. I can plug into the formula, but just knowing that they have the same concentration, if I have more liters of a solution that has the same concentration, I'm going to have more moles of particles. All right, so that's an important distinction. We could look at this example here, calculate the molarity for a solution where you dissolve 50 grams of calcium nitrate in enough water to make 2 liters of solution. If we're following our formula, I need moles of solute, and they give me grams right now. So we know this has to be converted to moles, and the only way to do that will be using the molar mass of my solvent, or sorry, my solute. You have to be able to write out the formula correctly to do that if they don't give it to us. So that's calcium nitrate. We can then find the molar mass of calcium nitrate. If we add up 1 calcium and 2 nitrogens and 6 oxygens, we should get something close to 164 grams per mole. We can take our 50 grams and set up a dimensional analysis conversion to convert grams of calcium nitrate to moles of calcium nitrate. Grams cancel. We should get 0.3 moles. And now that I have moles, I can plug into the formula. Molarity is equal to moles per liter. I go back and check. They did give me 2 liters, right? So my unit was liters. If they gave me milliliters, I would have to do another conversion. 1 liter is equal to 1,000 milliliters and just set that up. But I can plug right in, and we should get a molarity of 0.15, uppercase M, 1.5 molar is how we read it, okay? So 0.15 molar means that I have 0.15 moles of calcium nitrate in every liter of this solution that we have, okay? We talked briefly about ionic versus molecular solutions and the differences that happen when those solutes dissolve. Ionic solutes behave differently from molecular covalent solutes. Ionic compounds dissociate into ions, right? So as an example, when sodium chloride dissolves in water, we get dissociation to happen, which means that the Na and the Cl ions split up from each other, right? So one formula unit of NaCl splits into 2 ions, Na plus and Cl minus. So that means if I have a 1 molar concentration of NaCl solution, what that really means is that I have 1 molar of Na plus ions and 1 molar of Cl minus ions, which means together I actually have 2 molar of ions total, right? Because it splits into 2 ions. Molecular covalent substances, so for something like sugar, C20 or C12, let's say it's sucrose, C12H22O11, when that dissolves in water, there's no dissociation that happens. Okay? These sugar molecules, starting as a solid, will move apart from each other and become aqueous, but those molecules themselves don't break any further down. That's an important difference from molecular covalent substances compared to ionic. So if I have 1 molar of sucrose, I have 1 molar of solute particles floating around there. No ions, because there's no ions in something that's molecular covalent. But if we're looking at like how many total particles are floating around, it's still 1 molar. They don't break down anymore. If I have a 1 molar solution of NaCl, the total number of particles floating around there is, or total concentration of particles, is actually 2 molar of ions. Okay, so the key idea here is that the total particle concentration depends on how many particles are produced when the substance dissolves. Ionic compounds produce multiple ions. You have to be able to figure out what those ions are when it splits. That's just knowing how to write the formula and how many ions exist. Whereas molecular covalent compounds remain as whole molecules. Okay. All right, we looked at preparing solutions also. This is one of the last things we did. So if you're asked to prepare a solution with a specific volume and molarity, there are a couple of steps. So if we want to prepare, let's say, 500 milliliters of a 2 molar solution, the first thing that we have to do is we have to find the moles that we need to dissolve, moles of solute. And in order to do that, I need to use my molarity formula, but I have to make sure that my units are correct, right? It's in moles per liter. So I have molarity. I want to make a 2 molar solution. I'm going to find how many moles of solute I need. Liters is 0.5 because I have to convert the 500 milliliters to liters, right? And then I cross multiply and I get that there's 1 mole of solute that I need in this solution. Now, our balances don't measure in moles. The mass of a mole depends on what the substance is, right? And what particles make up that substance. So the next thing that we would have to do is, depending on what the solute is, and in this case, it's this substance, we would have to calculate the molar mass, convert moles that we figured out here to mass. That enables us to go in the lab, go to a balance, measure out the solute using a scupula and a weighing boat. Once we measure out the mass of the required solute, we're going to go grab a volumetric flask, right? That was a very important piece of glassware that we went over. You're going to pick a volumetric flask that is the size of the solution you want to make. So if I want to make 500 milliliters of solution, I'm going to go grab a 500 milliliter volumetric flask. We're going to add the solute to the flask. We're going to add a little bit of whatever the solvent is. In this case, they're not making an aqueous solution. They're making a solution where the solvent's ethanol. We're going to add a little bit of solvent to make sure that all the solute dissolves. And then once we have ensured that all the solute has dissolved, then we could add the remaining solvent up to the calibration mark that indicates that one volume that the flask reads. Okay, so that's important. The important reminders here is that we don't want to measure out 500 milliliters of the solvent first and add the solid afterward, right? Because doing that is going to result in a volume that's greater than 500 milliliters. And we want a volume that's exactly 500 milliliters. So add the solute first, dissolve it, then add the solvent until the total solution volume reaches whatever that desired mark is.